Welcome. This video introduces the concept of a singly linked list. This is a data structure that's a little bit complicated, so we've broken it up into a few parts. A linked list is a data structure for a list of elements, so it's an alternative to a vector. We've seen in previous videos that a vector holds a collection of elements and it uses one array object to store all the elements. And that makes some things simple because the vector data structure just has one pointer, so we need to allocate one array object when the vector is created and delete one array object when the vector is destroyed. There's a drawback to this, which is that an array object has a fixed size, and occasionally that array object gets over full, and we need to do this resize operation where we make a bigger array and copy everything over, and that's slow and maybe a little bit inelegant. Also, adding and removing from the front is a linear time operation due to scooting, so to speak. So if you wanted to take an element out of the first position in an array, that would kind of leave a hole there, and you have no choice but to copy every element over. I call that scooting. It takes linear time because it's a loop that visits all of the remaining elements. A linked list is an alternative, and it takes a different approach. Instead of having all of the elements in one array, instead, in a linked list, every element has its own object. And we call one of those objects a node. So every single element is in its node object. There are many node objects, which means there are many pointers in the data structure and many new delete operations. There's no resizing ever because this is a much more finer grained data structure. We can break off one little object for one element or add one little object for one element without disrupting the others. So we never have any resizing to deal with. And an advantage of that is that the operations take a consistent amount of time because there's no unusual slow operation. So we don't have amortized time bounds on these operations. A downside to that is that there are higher constant factors, which means that while the major operations of adding and removing to the front or adding to the back of a singly linked list take constant time, the constant factor on that is higher, which means they're slower than the corresponding operations on a vector. And that's because new and delete are relatively slow operations. Okay, let's just get the idea of a linked list across. This is linked lists in general. So every element is stored in its own node object. So we draw each node as a rectangle here. This is an example of a linked list containing the elements 7, 1, and 4. And every node has to have that one element. We'll use a template parameter t for the data type of one element. So every node has one t object, and it also has a pointer to the next node. And this is why we call this linked. Those next node pointers are sketched as these arrows. And so we can envision that there's a first node containing the number 7, and that node has a next pointer to another node object that contains a 1. The 1 node has a pointer to a node object containing 4. This has to end somehow, and the 4 node has a pointer to some kind of end object. So we need some way of distinguishing between the end. There are two alternatives for a node. It can point to yet another node, or it can point to the end of the list. And that needs to be distinguished somehow in programming, and there's different ways of doing that, and we'll get into that in a moment. So the overall list object then needs a pointer to the beginning of this thing, and there's a convention of calling that a head, the head of the list. And we also might need to distinguish between empty. What does this head pointer point to if there are no nodes at all because the list is empty? That needs to be handled somehow. And sometimes there's another pointer to the tail, as it's called. If the head is the front, the opposite in the analogy is the tail at the end of the list. Finally, we have our list. Remember its size. It has a size t size data member to keep track of how many nodes are there so that we can tell if the list is empty very easily. Now, there's different programming approaches for representing the concept of the end of the list after the last node and the concept of the empty list where the head pointer points, and we'll talk about that soon. Finally, the analogy here, I guess, is like a snake. This is my beautiful drawing of a slithering snake here. So you can imagine the head is at the front, the tail is at the back. It just helps you keep head and tail straight. Okay, the design approach we're going to use in our class is a circular linked list with a dummy node. This is the answer to how we represent the concept of the end of the list and how we represent what the list points to in the event of an empty list. So this involves this concept of a dummy node. It's not the most polite phrase, but it's kind of what it's called. So a dummy node is a node that's just there as kind of a placeholder. It does not actually store an element. So it has the right data type for a node. We can have a node pointer point to this dummy node, but it does not store an element. It's just an extra there as kind of a placeholder. And we will place this one dummy node always before the first real node. So here I'm sketching a singly linked list that contains 4 and 5. 4 is the first real node that actually has an element in it, but to the left of that, there's this dummy node that's just there to keep the list organized. This approach of a dummy node avoids a null pointer. Another approach is to have the last next pointer point to null, but then you have null pointers in the code, and there's a possibility of null pointer exceptions, and also you have to remember that you have to have if statements that look for null pointers all over the place. Those if statements can slow the code down. So some designers prefer this dummy approach because it makes the code a little faster and we don't have null pointers to worry about. Okay, the circular part of the design is that the last node points to the first one, which would be the dummy node actually. So the tail node here containing element 5, it needs a next pointer and it points back to the dummy node, so it loops around to the beginning. So we have kind of a circular situation here. You can imagine if we keep following these next pointers, we're going to spin around forever, and our code needs to be careful not to do that and get stuck in an infinite loop. So you could think of this as kind of wrapping around back to the beginning. So the list object has a pointer to the tail node. You know, we could have a pointer to the head node. It turns out to be more convenient to have a pointer to the tail node. We'll see why that is in a little bit, because we want to be able to get to the last element efficiently. And in the event that the list is completely empty, this list object's tail pointer points at the dummy node. Now, note, we can always find the head node. It's a little bit convoluted, but we can do it. If we want to find the head node, we go tail, so follow the tail pointer, go to the next node. The tail's next is always the dummy, and then the next from the dummy is always the first element that actually has an element in it, the first node with an element. So again, in order to locate the first node with an element in it, we go tail, next, next, and that takes us to 4 in this example. Okay, so here are a couple sketches of valid linked lists using our system. Circular linked list with dummy node. On the left is a linked list with 3 elements, 7, 1, and 4. So I've got the dummy node first on the left, and then the 7, and then the 1, and then the 4. These next pointers, each node points to the next one to the right, and then the very last node points all the way back to the dummy. That's the circular node link. And the size is 3, don't forget about the size, and tail points at the last node, the 4. All of these definitions work for an empty list as well. It's an important case to consider. In the event of an empty linked list on the right here, size is 0, of course. Tail points at the dummy node, and we still follow the same rule. The last node points back to the first node. They happen to be the same thing here, that the dummy node is the last node and also the first node. So you've just got this one pointer pointing around in a circle. A little bit weird, but it makes the operations on empty lists work consistently. Here is one way we could declare the data members for this linked list. So on the left, I have the singly linked list class. It's a template class. T is the name of the data type of one element. And I've got a shared pointer to a node object called tail. And that's illustrating this tail pointer here. We need to use shared pointers here because there can be more than one pointer to the same node. And you can see that right here at the tail node. So if we look at these nodes, how many incoming pointers are there? The dummy has 1 incoming pointer, 7 has 1 incoming pointer, 1 has 1 incoming pointer, but the last node, the tail node, has 2 incoming pointers, one from whichever node came before it, and another one from the list's tail node. That's actually true also on the empty case. The dummy node has 2 incoming pointers, the tail node of the list, and then its own next pointer points to itself. So these need to be shared pointers since there can be multiple pointers to the same object. And we've got the size as a size t integer. Here's how I could declare a singly linked node. SL is for singly linked. It's a template class again. It has a t element. That's the data we're actually storing, in a way the most important part of this. And then it also needs a shared pointer to the next node. And we have accessors and mutators for the element and the next pointer. Okay, let's clarify the invariants on this. It's a little bit complicated, so the invariant term is helpful. These are the rules that a singly linked list needs to follow to work properly. Every node has to point to the next one. So in my sketch, you see that every node is pointing to the node to the right. We don't have these pointers skipping over nodes or missing them or something. And the rightmost node points to the leftmost node. So every node points to the next one, and then the last node, like the 4 in this sketch, points back to the first. That's the circular idea. The dummy node is between the last and the first elements. So prior to the first element 7 is the dummy node, and then after the last element 4 is the dummy node. And the size is accurate. It's a minor detail, but it's worth remembering. This has 3 elements in it, so size has to be the number 3. I'll mention there's some alternative ways of doing this. We're going to focus on the one circular linked list with dummy node. But there's the singly linked list alternative we're looking at right now. It's called singly linked because there's one pointer between any 2 nodes. A doubly linked list doubles that to have 2 pointers between 2 nodes. And we're going to cover that later, but for now we're focusing on singly linked. There's some implementation details within the world of singly linked lists. For one thing, does the list have a size data member? We say yes, which means you can get the size of the list in constant time. We could say no, which would make the list take less space, but it would take linear time to compute the size. You'd have to count all the nodes in a loop. How does the list point at the beginning or end of the nodes? It could point at the first one or the last one. There's trade-offs. We say that we point to the tail node. And how do you represent the end of the list? We say that we have a circular pointer. That's one way. The last node points back to the first one. That's how you can tell when you've hit the end of the list. You could also use a null pointer for the last pointer. That can work as well. Okay, I recommend that when you're working with linked lists or really any data structure with a lot of pointers, that you make a checklist for the pointers that need to be updated in an operation. You know, a checklist is this idea of a to-do list, and it's important in safety critical situations. So for example, every time an airplane flies, there's a pre-flight checklist, and a technician or the pilot needs to double check that every part of the plane works. They do this before they fly. You know, it's critical. You don't want to get up there and find that some important part is broken. So you know, why do we do this? Pilots are good at their job, technicians are good at their job, because it's human nature that it's easy to overlook one detail, especially when you're doing the same thing over and over again. It's just how the human mind works. So checklists help us not miss details, and I recommend them for this kind of thing when we're writing a linked list operation. Writing a linked list operation involves moving a lot of pointers. There can be many pointers that need to be updated. All of this business of tail, next, all that kind of thing is kind of inherently confusing. And a way of getting around that is to make a checklist. It's easy to overlook one of these pointers. If 6 pointers need to be updated, maybe you write code that does 5 and it doesn't work. So here's what I recommend. Make a sketch of the operation you're trying to do before and after. What should a data structure look like before the operation and after? Identify the relevant pointers. I'm going to be highlighting them with colors. You could circle them, whatever. Make a list and count them. So there are 3 pointers that need to be updated. Here they are. Here's the list. You write your code or pseudocode to do the operation, and then double check your list of pointers. Look at your code. If my list has 3 pointers, is item 1 updated properly? Is item 2 updated properly? And is pointer 3 updated properly? If any of them are missing, it's not correct. Okay, next video we'll get into doing this with some of the linked list operations.